Good afternoon. Good afternoon, everyone. This is algorithms. This is ranges. This is all excellent code from the library, and the compiler definitely understands it. But the question is, does anyone else? My name is David Sackstein. I'm an independent consultant, developer, and instructor. I work with C++ and with other languages. And I'm passionate about writing clean code. So this is the topic of my talk today. Let's begin with a little discussion about the standard library. So the implementation of the STL, or the standard library in general, has APIs that are extremely well designed, thoroughly reviewed. The APIs are consistent, and they are compatible over many different platforms, compilers and hardware platforms. They are as efficient as possible, and they actually do comply with many, or maybe even all, of the core guidelines, core CPP guidelines. However, classes and functions in the library are generally very long. The cyclomatic complexity of many of the functions is very high. Cyclomatic complexity refers to the number of different paths that execution can flow through a function. When the complexity is high, it makes it more difficult to reason about and more difficult to test. Header files are very long. Chrono has almost 6,000 lines. Algorithm has over 9,000. They make excessive use of macros and compilation flags, and some of the code is very repetitive. So we really have a dilemma here. When I speak to people about clean code and how important it is, people say, well, I write like the library does. Big functions, long header files, everything works. So I need to resolve this problem. People tell me, we don't need clean code. It's not something that we apply to the code that we write today. And I think we need to understand that clean code means different things in different contexts. And in most of the contexts that we find ourselves writing code, clean code is very important. So what I'd like to do today is, first of all, discuss just a little bit about clean code in context, to understand a little bit more about the pressures involved in making something clean and the benefits. But immediately following, I would like to introduce you to what I consider the basics of best practices for C++ programming. This is not going to be the main part of the talk because there are many, many details, and I just want to give an outline. So one slide will be enough. The main part of the talk will be to develop an application, a very small application that I built for this talk, which will be developed from step to step. I'll take a few wrong turns and clean up what I've done. And along the way, I expect to be able to learn a few lessons and give a few tips. And towards the end, we will be able to summarize, and I'll be able to summarize those tips, those lessons learned. Following that, time permitting, I'd like to open for discussion. I would actually prefer if questions are asked at the end, because we can have a very, I believe, productive discussion about some of the concepts that I'm going to present today. Clean code is not something which everyone has the right answer to, and there are many opinions. It's quite a contentious subject. So I think I would like to make sure that we do have time for the end where we can make a discussion of this and maybe learn some more from the audience. So that's the plan for today. Let us start off with what I described as context for clean code. So the benefits of clean code are very clear. We need clean code because if the code is readable, then it's easily reviewed, it's easily testable, and it's maintainable, and it can be extended easily. The benefits are pretty obvious. However, there is a cost. From my own personal experience, I find that once the code runs and the tests pass, there's still at least another 50% of the time involved to make that code as clean as possible and ready for review. So there's a cost. And that's not the only cost. Sometimes certain constraints can't be met when clean code is implemented to a full extent. So what I presented here is almost like a visualization of the development environment that we work in. And to understand how clean code is applicable at each layer. So at the very lowest layer, we have core library code, like the code that we saw earlier in the presentation. That would include core libraries like the standard library. And then above that, we have project library code or third-party components. And above that, components that we write and applications above that. Each of these may comprise of other layers. But there's a stack that we build upon. And I think you will agree that as you go down the stack, the implementations are generally more stable. You don't get weekly releases of the STL, or even of third-party code that you use in the layer above. The lower down you go, the more stable the implementations are. And therefore, the reviews that are done on that code are generally more thorough. You will often find, as is the case with the STL, that maintainers and developers of those layers are more expert than we find in the industry. And there are also very specialized constraints as you go down the stack. So in the case of the standard library code, we need to retain backward compatibility. We need to have multi-platform support. It needs to run on a number of compilers in the same way. And we need efficiency. So all of these specialized constraints build up as you go down the stack. And all of these point in the direction of changing the approach to clean code. We can't necessarily apply the same rules to code that is subject to these constraints. However, on the other side, we can see that as you go up the stack, and most of us are above the bottom layer, the benefits of readability remain and the excuses diminish. Because in the usual environment that we work in, there are many releases, and code is revisited many times. We have agile, and we have 2 weekly sprints, and code is revised many times, and there is a change of requirements, and there is maintenance to be done, and bug fixes to be done. So as we go further up the stack, we're in a much more dynamic environment, and it's actually there where the requirement for readability is so much more important. So my conclusion at this point is that we do have an answer. Okay? Don't necessarily learn from the library code everything. There's a lot to learn, but clean code is something that has different requirements or different trade-offs at different layers of the stack. So what, in fact, are the best practices for software design? As I said, it's going to be one slide. I decided simply to take the tried and tested acronym originally coined by Robert Martin and Michael Feathers over 20 years ago, I believe. And even though I don't think these are the 5 commandments, and there are other principles that we add and we know are important, and some of these are less important than the others, but if I have to put it on a slide, I would say this is our best bet. These principles give a very good guidance into how to allow object-oriented languages or coders of object-oriented languages to produce code that is decoupled and therefore is capable of being testable, extensible, readable, and everything we need. So let's review them very briefly. Single responsibility principle. We like our components to be small and to have one responsibility. That's not only classes, it's also functions. In my opinion, it's also files. And why do we want them small? Because when they're small, they're easier to reason about. They're easily testable. And what's not always so obvious is that they're much more reusable, because small objects can be composed into large objects and bigger systems. The second principle is the open-close principle. It's a little bit of a play on words. It really means, it was intended to mean open for extension, closed for modification, which means that the code that we write should preferably be stable in the face of extensions later on. Now, of course, if someone changes the requirements of our code, we need to change our code. That's fine. But if someone wants to add something to use with our code, we shouldn't need to modify our code. And the solution for that generally is to use abstractions at extension points or at potential extension points. The third principle, the Liskov substitution principle, is a bit difficult to pronounce, and it's also a little bit difficult to explain. but I'm going to map it later on in the course, in the talk. I'm going to map it to a comment that's made in the CPP core guidelines. There's a comment that says, differentiate between implementation inheritance and interface inheritance. And this is exactly what in my opinion, what this principle is talking about. And we'll see the example later on. The interface segregation principle is really a bit redundant, in my opinion. It's really just repeating the SRP, the single responsibility principle, but for interfaces. And finally, the dependency inversion principle tells us a lot about how to compose objects. And I must say that in C++, I've always had a problem that I haven't been able to implement composability of objects in the same way as is possible in C#, .NET, Java, and in other frameworks where you have a very powerful dependency injection framework. I haven't found easy implementations of dependency injection in C++. What I'm going to propose today at the end of the presentation is a response to the dependency inversion principle in C++ as well. I believe this is not the only presentation on dependency injection, but dependency inversion principle speaks about dependency injection, and it is possible to do in C++. But this is not all. These are the 5, let's say, basic principles, but they are very general, and they apply to most object-oriented languages. But we have specifics for C++. They are, of course, the C++ core guidelines. It's a very large document. The authors of the document, they actually say you don't have to read it. It's not bedtime material for reading, but rather it's referred to as a reference. I would actually suggest that even though you don't have to, it might be a good idea to read the thing from cover to cover. Because I've found that when you read vast amounts of this document, you understand better the philosophy behind the document itself. So you may not remember all the details, but they will certainly ring a bell when you see them, and you may even adopt them yourself without even reading the details. So this is the groundwork. With our presentation, our talk today is more about the practicalities. So as I said, there's a project that we're going to build. This is a link to the GitHub repo that I've prepared. I've called it Clean It, for obvious reasons. And it's a very simple project. Along the way, there are a number of commits that follow more or less what we're going to do here in this presentation. I have marked particular turning points with tags. And I mentioned the tags here in the presentation, so anyone who's interested to see the code in more detail, you're welcome to clone the project and look at the differences between the different tags and see what's been changed from tag to tag. And that way you'll appreciate better the detail of what I'm talking about here. So, what actually are we building? We're building a VOD application, VOD standing for Video on Demand. I'm not actually going to be doing VOD. What I really want to do is just build a structure that allows us to discuss interreactions between objects and the structure of the code that implements those objects. So we're going to develop a movie reader, which is simply an object which reads files from disk and allows a video server, a VOD server, to present the list to a connected user and allow the user to select one for playback. So that'll be the VOD server and the VOD client. Actually, the VOD client is not part of the project. It originally is, but it's not going to be later on. The VOD client is actually intended to be a test tool. Whenever I'm told to write some sort of server, but don't worry about the client, we'll do that, I always write the client as well. Because in the true tradition of TDD, if you really want to make sure that your code works, there's no really other way but to test it. So testing with a VOD client will enable us to understand if our APIs were implemented correctly. So the first tip is use the compiler and use tooling. I found it very useful developing this application. We always use the compiler anyway, but we know very well that the compiler can also produce errors. I recommend turn on the warnings as errors. And set a fairly high level of warnings. I use warning 3, which is the default in Visual Studio, and it'll tell you a lot about your code. In addition, I recommend you use clang tidy, but not only to use it once in a while or at the end of a build, but to use it interactively. take a tool that will do so either as a plugin to Visual Studio or a plugin to Vim if you're using. I've been using ReSharper with Visual Studio. ReSharper is a very powerful tool. In the past, it's been mostly for C# in .NET, but I found that recently it's been a very, very powerful addition to the toolset for C++. And in fact, ReSharper, by default, will provide warnings and inspections that derive from Clang tidy warnings, and will also offer fixes for them. And the reason that I say use it interactively and not just at the end of a build is very simple. When you use a tool like this interactively as you code, then apart from cleaning up the code, you can actually learn quite a bit from the process. So what does our solution comprise? As you can see, there is a solution up on the top with a very simple layout. It just has a moviereader.cpp at the first, a moviereader.h, and the main is where I put the test, just to get things going. The test simply reads the movies, checks that there are 3, and succeeds. Let's take a look at the first implementation file, the moviereader.h. As you can see, I'm noting that there's something missing. What's missing? Anyone can tell me? Sorry? Vector, yes, of course, vector is missing. And that's because in the public API that I'm proposing here, I'm returning a vector of movies. So if I don't put vector here in the header, then someone's going to have a headache and trying to understand why moviereader.h causes his code not to compile. Now, this is not so much of a problem with vector because everyone knows what vector is, but it could be a problem if you're relying on some company code in a large code base where there may be many definitions, and the user will have to rack his head to understand where the definition lies and which include file he needs to put in his code to make sure that your code will compile. So let's talk about headers. There are a few things I think we need to remember when building hierarchies of headers. First of all, a header should always include all the headers it depends on, just like in the case we just seen. Second of all, a header should not include any headers that it doesn't depend on. And the reason for this is that it would increase otherwise the dependencies and the coupling that your user, poor guy, will actually have when using your code. If, for instance, you're using boost, and that's in your headers, then he needs to use boost. But if it's not really required, then why does he have to find in his include path the boost headers? There's a problem, actually, with header files in C++, because if you have an implementation that actually uses boost, as an example, then even though it's not part of the public API, you will actually need to expose the header according to the first rule. A header should actually include everything it depends on. So we should try to avoid this as much as possible. If you have a private member or a private method that actually uses something that the user does not need, then use one of the idioms that allow us to hide the details, the pimple idiom, for instance, or simply use an interface. Both of these will alleviate the need to include the specifics of the type that you're actually going to be using in your CPP file. Separate internal headers from API headers, that's obviously very clear, because you don't want anyone to be able to see. You don't want your internals to leak outside where people are using your code. So if you look at the repo, the git tag v2 header ordering, I've made those changes, and we can move to the next step. Let's have a look at the implementation. Oh, modules. I haven't mentioned modules so far, but of course modules are one of the solutions to managing headers. And why is that? Because one of the problems we're trying to avoid is leakage from one header to another. Modules actually solves this problem because you explicitly export from a module. But having said that, I still think that even after we use modules extensively, we will still need to organize our dependencies in the way I've described. So indeed use modules, but keep in mind these guidelines for building the headers and the header units that you create. So if we look at the implementation code, yes, I know it's very difficult to see the detail. That's not really intended to see the detail. What I'd like to tell you about is that this function, the read movies function, actually does many things. It loops over movie files. And then for each file, it opens a file, it reads a line, it passes the line. It's very, very complex. And I would say this code is very unclean. In addition, as if to compensate, there are comments littering the code, which seem to say, this is what the code is doing. Comments that tell us what the code is doing are usually bad comments, and we should try to avoid them. The solution is simply to extract functions so that each function does one thing, and then the need for the comments goes away. In addition, there is a problem in this implementation of error handling. And the problem is that the actual code itself occurs somewhere in the middle of the function. Everything else is all about errors. And in addition, these errors are exceptions. Now, there's nothing wrong with exceptions. There are many reasons we would like to use exceptions in many places. But in this particular case, there is a problem with using an exception. If you're inside the loop and you throw an exception, then you don't complete the loop. So this may be a violation of some requirement. If the intention was to read all the files that can be read, then of course we're not meeting that requirement because we threw an exception in the middle. So what I would like to propose as a guideline is only to use exceptions for the exceptional. This is a well-known guideline, I'm not inventing it. Only to use them for the exceptional. When you use them for the exceptional, and of course, the obvious thing to do is to terminate the application or to cleanly exit the application, but there's certainly not much you can do at the local level. What can we do for exceptions that are not exceptional? For instance, I can't open the file, the user input is not good enough. It doesn't meet it doesn't meet the validation requirements. These are not exceptional errors. These are errors that we tend to encounter all the time in the course of our business logic. So for these, we don't have to use exceptions. In fact, we probably shouldn't. What should we use? Well, until now, we haven't had a solution. But as a number of lecturers have mentioned in this conference, std expected is expected in C++23. And this is actually going to help us solve this problem. How do we handle exceptions that are expected exceptions? I mean, they're called unexpected, but they are, in a sense, expected. They may happen during the course of things, and we need to be able to recover from them. So std expected has been around for a long time. It was originally proposed, I believe, by Andrei Alexandrescu in 2012. It became a proposal in 2017, and I believe it will be accepted in the, by the Standard Committee for C++23. What is standard expected? It's a class template which has a T and an E. A T represents the expected value type. The E represents an error condition. You can define an E as an exception, or you can define an E as a string, as I will do in this project. You can think of an expected as a variant, but it's an opinionated variant. It doesn't deal with T's and with E's in the same way, because the natural way to deal with an expected is actually to bias towards the T. We'll see that in the code as well. Now, as it isn't in the standard, I've used a public implementation by cbrand. I'm going to refer to it as TL expected. That's the name of the namespace that he uses. It's a very good implementation because not only does it actually implement the specification of TL expected, but it also adds some methods that will be useful to help us write cleaner code. I'll be showing those in just a moment. So moviereader.cpp, if you look at git tag v3 with TL expected, you'll see that I've split up read movies into two functions. There's read movies, and then there's read mov, which handles the single file name. And as you can see, this function no longer throws exceptions explicitly. Instead, it returns an expected of something. The something is a vector, and the vector itself is of an expected of movies. And that's simply because errors can occur at the outer level and the inner level. It looks a little bit verbose. It'll look better later on. And then, if we look further down the file, we'll see the implementation of read movie, which is a single read of a movie. Now, I consider this cleaner than the original. I hope you'll agree. Let me tell you a little bit about what's going on here. Read movie no longer throws exceptions explicitly. It returns an expected of movie. An expected here refers to a TL expected. And as you can see, it's like a workflow. It opens a file. If that's successful, it tries to read a line. And if the line succeeds, if it manages to read the line, it'll then go forward to pass that line and detect metadata information about the file. Basically, it's reading an integer from a string. And if all of that succeeds, it will return a movie, just like before. But along this path, exceptions can occur. They won't be thrown. They will just be added as strings along the path to return an expected. And what's nice about this style of programming is often referred to as railway-oriented programming. It teaches us basically that there are two tracks of operation. There's a track which is the expected, the T, and there's a track of an error, the E, and we never create expected of expected of expected along this path. We always use methods like and then, which is provided by TL expected, to compose functions which operate on previous outputs to be able to create an expected of the type rather than expected of expected. So the mechanics, I invite you to take a look at the implementation. The mechanics are quite interesting. But basically, this allows us to break up the component into pieces. If you look at the implementations of each of those files, you will see that now each of these files does one thing. Open file opens a file or fails. Read line reads a line or fails. And pass movie passes that line or fails. Let's move forward. One of the problems that I would say we have with our movie reader is that if there are 10,000 files to be read, it's going to put all those 10,000 files in a vector. And this is a functional problem. It may actually be a cause of one of the errors that may occur here, which is a bad alloc. So we can do all we like to prevent throwing exceptions, but if there's going to be a bad alloc, then we may fail, and the exception will be an exceptional exception, but we're not catching it. So one of the things we can do to ease the use of memory, this is not going to solve the error problem, we'll come back to that, but one of the things we can do to ease the use of memory is simply to use a generator. We get generators in C++20 because generators are an abstraction over coroutines. And what generators allow us to do is to iterate lazily. This means we don't actually have to store all the iterated objects in memory. And in addition, it offers a sort of a decoupling between the iterator, which itself is implementing a loop, and the user of that iteration, which can write its own logic outside the generator to handle each of the iterated objects. So a generator is a very, very well-known concept, and it's been implemented over coroutines by libraries. The recommendation, actually, of the committee and the community is not to write our own coroutines always. You do so when you want to do something very specific, but as in most cases, if there's a library available and you can use it, and it's a good one, you can use those abstractions from the library. So I've been using CppCoro. I'll just mention a word about CppCoro as a library, not so simple. But just to mention that once you're using a generator and you're returning a generator, you can actually, the generator written by CppCoro is actually a range as well. So you can use range functions in your test to verify that the generator is actually generating values for each of the movies. So the recommendation here is to use generators for lazy iteration. That's not the only reason to use generators. If any of you joined Daniela's presentation yesterday, she demonstrated how very, very highly nested iterations can be simplified by simply co-yielding inside the loop. And again, this cleans up the code very much because it saves a lot of complications of handling the state of the iteration outside the loop. So generators are a very, very useful tool that we can use quite easily today in C++20. But I recommend using a library. The famous CppCoro library, as I mentioned, by Louis Baker, unfortunately is not being maintained. I may be wrong, but the last time I looked, it wasn't being maintained. So I actually used the fork of this library, which you can also take from here, by Andreas Burr. It does support C++20. In other words, it doesn't use the experimental headers, it uses the C++ headers. And it also fixes a lot of bugs, and I've incorporated it into the library. One more improvement I'd like to make for error handling. I mentioned that bad alloc may happen. In that case, an exceptional exception is thrown, and that's the kind of thing we need to handle somewhere. So in order to fail fast, if we want to fail fast, the best way to do so is to, or the best way, but a possible way to implement to do so is to do a try and a catch. I wrote in the code a simple method called expect, which what it does is basically converts a try-catch to an expected value. And once I use that, I can truly mark my methods that use expected as no except. Okay. The next thing I'd like to talk about, if you remember, is the movie.h. The movie reader.h. The movie object itself used a string and an integer to represent what the movie is. It's basically a name and a duration. And quite audaciously, I mentioned in the code that this int is a duration. But how is a duration an int? Is it seconds? Is it hours? What does it refer to? And there are more problems with these definitions. These problems are related to something called primitive obsession. And it's a common smell in a lot of code that I see where programmers represent some concepts instead of by an object, they're represented by a primitive, by a string, by an integer. And this is usually a bad idea because strings and integers can have values outside the scope of your domain. Now, even if you're going to use the chrono object seconds to completely disambiguate the meaning of duration, I think we have a crash here. Frank, can we move to the backup? Great. So, even if you're using seconds from the library, you're still not definitely validating that those seconds are not negative, or they're not too many seconds in the duration of a file. Primitive obsession is a code smell in which primitive data types are used excessively to represent data models. In our case, we're using an int to represent seconds. Movie itself does not validate its invariance, so the duration could be any value. But we can fix this, and here is a tip to fix it. What we can do, as you can see here in the code, is to make movie not just a simple struct, but actually to make it into a fairly clever object. This clever object has a non-default constructor, which is private. And therefore, the only way to create an object of type movie is to use the static factory method that has been provided. What actually is going on here, if you look at the bottom, you can see that the movie constructor will throw an exception if the invariants of the class are not met. So if the duration is negative or it's above a certain value, then it will throw an exception. Why is this important? This is important because anywhere you see a movie structure in my code, you know that it's valid. There's never any reason for anyone to introduce validation code to clutter up the functions. So it's a very important concept to be able to write an object that is always valid. Now, if indeed an object was created, or an attempt was made to create an object with incorrect values, then this constructor will fail, it will throw an exception, and the static factory method will actually use expect to catch the error and return unexpected. So this is how I've solved the problem of primitive obsession, particularly in the case of movie, in the presentation, in the document, in the project. So if you look at v5, avoid primitive obsession, you can see that implementation. Now let's go forward to the actual interesting part, the video server itself, the VOD server itself, and the client. As I said, the client is going to be part of the test, but for the moment, it's all together. So the VOD server is going to use the movie reader to stream movies to clients. It's going to call back to the client to notify of the start operation of a movie playing or a movie stopping. We could use it actually also to send out the time code of what actually is going on now in the streaming of the movie. In order to do so, it's using a weak pointer. You might want to have a take a look at that. There was a very good presentation yesterday by David Olson, who spoke about smart pointers and mentioned weak pointer as well. A weak pointer is a way of preventing cycles when using shared pointers. This is a case in point, and it was required in this implementation. A weak pointer is actually a reference to the original shared pointer that doesn't extend the lifetime of the shared pointer, and it's a typical usage of weak pointer to use the observer pattern to notify a client who may or may not be there. The client itself may call connect, disconnect, play, and also get movies to get the list of movies that he's able to play. Okay? There's a state machine inside the VOD server, a very simple state machine. I don't think it needs much explanation. And that's been implemented using a flag. Let's have a look at VOD server itself. This is the header file. Again, I'm not quite sure if you can see it from the back. And therefore, I'm just going to read out what you see on the right. What's going on here is that the VOD server itself relies on something called the console logger. And the console logger is an implementation detail, and yet it inherits from the logger. Implementation inheritance is not recommended, and we'll talk about that in a little bit more detail later on. But there's more going on in this file. If you care to take a close look, you'll see that there are many definitions inside this file that the implementation of VOD server relies on. It relies on something called an iMovie observer, which is an interface that is used to call back to the client. That's fair enough. But why does it rely on the console logger, and why is that in the header that is being exposed to the clients? So there's too much going on in this file as well. In the implementation is a grand violation of the single responsibility principle. If you take a look at the function play, for instance, this method is testing the state to make sure we're in the play state. Then it's opening a thread, and in the thread it's doing the streaming in the middle between line 63 and 70. It's a very sophisticated streaming mechanism. I'm waiting on a condition variable. But before so, I'm trying to get the client, trying to get a shared pointer to the client and notifying it that we're starting, and at the end, notifying that we're ending. And all of this is happening in one lambda, which is being inserted into a thread, into a J thread, inside one function, and everything is done in one function. So play does too many things. It manages state, it starts a thread. The lambda itself is doing too many things. It manages notifications, it does streaming. This is a violation, in my opinion, of the single responsibility principle. Makes the code not so clean. So the next step in the presentation, in the repo, in the project, is a refactoring step. I minimize the APIs, so VOD server does not actually get exposed to the users, but rather an interface to the VOD server gets exposed. The iVOD server itself, in its definition, has no mention of console, of loggers, of anything of the sort. And each interface that I'm defining is defined in its own header. Now, many people disagree with this. I'll be happy to hear about what your opinions are of this. It generally creates many, many files. But I believe many files doing small things is simply an example of using the single responsibility principle. And it does allow components to be decoupled from things they don't want to depend on. In addition, I've defined a factory method that returns an iVOD server. So anyone wanting to create a VOD server only needs to provide the inputs and get an interface. Of course, the interface is provided as a shared PTR because the intention is that the lifetime should be controlled by the client, or at least by the clients. I could have used a unique PTR as well. And in addition, I've done some extraction of the methods to make sure that each method does only one thing. And another point, which is very important, is at last, a separation of test and production code. So the Clean IT project now becomes a DLL. Could be a shared object if you're running in Linux. It has a binary interface, which is basically one function, which is the factory method mentioned earlier. And the interface itself is the only thing really that the client needs to know other than the function that creates it. And then there's a separate project which does the tests. And I placed the VOD client out there in the test project and not together with the production code. So there's some refactoring being done there. And that's being done, I believe, in V5, not V6. The next step is dependency injection. And this is a very important pattern that I'd like to demonstrate to you. It's a well-known pattern in many languages, and C++ as well. Let's talk a little bit about dependencies. If we have an object that depends on, let's say, an implementation of file, then it seems to be an encapsulated solution to have that object create the file when it begins in its constructor. But the problem with this is that if you want to test the object, you need to be able to access the file system. And if this is an object that's doing networking, you need to be able to access the network. And this makes testing very difficult. So a typical solution that we are aware of is introducing mocks. We'd like to introduce a mock in such a way that the code that we're testing is not aware that there's something different to what is usually done in production. So we create an interface. And when I talk about dependency injection, generally, I speak about constructor injection. There's a slide on that in just a moment. But constructor injection says that in your constructor, when you write your component, specify the arguments as interfaces that you need for your implementation. When you do that, first of all, you're allowing the outside world to control which implementations will be used. And second of all, you're making it very explicit. So it's very clear to see what your dependencies are. So this is the solution after all the changes. There's the movies, which is simply data. It's a folder outside of the projects themselves. There's cleanit, as I said, which is now a DLL. And there's cleanit tests, which references the DLL and implements the tests. And the only connection between the tests and the cleanit DLL itself is the factory function and the definition of the interface that the factory function returns. Once I've done that, you'll be able to see there are now tests that do VOD server tests, and there's a client inside the test application that connects to the client, connects to the server, and verifies that the server is behaving correctly. The VOD client, as I said, is part of the test project. Okay, but now we have a problem. The problem is that the tests run very slowly. You can run this particular commit and you'll see the tests run very slowly. The reason is because that conditional variable that I implemented as the streamer waits for the duration of the file. Luckily, the file has in it only the value 20, which refers to 20 seconds. So the test waits for 20 seconds to complete. And this is, of course, very bad. We would like to use dependency injection to replace the implementation of the streamer object that is being used by the VOD server. So now the challenge is to create a mock for the streamer and to make sure that that is introduced into the constructor of the VOD server object. So using dependency injection, we can decrease coupling between components and their implementations. The component doesn't care what implementation it uses, as long as it meets a contract. Components, of course, should depend on abstractions and not on concrete types. C++ provides two abstraction models. You can use compile time abstractions using templates, and you can use runtime abstractions using virtual functions. I've used the latter here. And in tag v6, you'll be able to see the setup of the interfaces that each object needs, presented as arguments to the constructor. So constructor injection is a very common way of injecting dependencies into an object. It does require the object to store a reference to the dependent object, which means that the lifetime of the dependent object needs to encompass, it needs to cover the lifetime of the object that's using it. We're using shared pointers, so there's no problem. The benefits are that the caller can decide which implementation can be used. Definitions, as I said, dependencies are explicit and easy to find, but there is a challenge. And this is a challenge that hasn't been so easy to solve in C++ until recently. The challenge is that composing objects then becomes complex because we've broken the encapsulation. We've allowed outside objects to decide how to build our objects. That means that the outside now needs to configure all kinds of, it needs to be able to wire up all these little objects and pass them as interfaces to other objects to build up the entire system. And this becomes very complex. This has been solved many times in Java, in C#. There are what we call IOC containers that handle all the complexities of this. And they rely usually, or often they rely on reflection, runtime reflection, which is something we don't have in C++, not out of the box. However, we do have compile time reflection. And that's something that can be used to identify what requirements a particular object requires in the constructor. And if we can determine that, we can build an IOC container that can do all the work of building the objects for us. So that is what we call an IOC container, an inversion of a control container. An IOC container resolves the challenges. It's a factory with two aspects. It allows you to register methods. In other words, you say, for this particular interface, I would like to see an implementation of this type. And you can do this for as many types as you like. And then there are resolve methods, which are used when the container is ready during the application, during the runtime. Give me, please, a logger. Give me a logger. I don't care what interface, what implementation you choose. Now, it's been registered as a console logger, so you'll get a console logger, but you don't really care. Now, why is this actually solving a complexity of composition? Because basically, you still need to do registration. That's still part of the flow. So why is it solving the problem? Well, if you actually build with an IOC container, you'll get the idea yourself. You'll notice that every time that you add a new interface or a new implementation of the interface, you will need to do a registration. But every time that you create an object that needs that interface, a new type that needs that interface, you don't need to do anything. Because from the point of view of the IOC container, any object which requires an interface that it recognizes and it can build will be created by passing in an object of that type. So what we get is that the number of specifications, the number of registration calls that the configuration code needs to call is proportional to the number of abstractions that you've defined or the implementations of those abstractions, but not to the number of types that actually need to be resolved. And this actually scales very well. You can actually build up your abstractions, registrations, usually ahead of time, and then you can build objects that use these implementations, many different types that the IOC container actually doesn't know about, but will be able to build for you simply because you've registered the types that are required. So how can we do this in C++? I've been meaning to test out this framework for some time. Didn't get around to it, but I did prepare it for this presentation, and I'm very pleasantly surprised. It's called hypodermic, which is a pun, of course, for injection. And it resides at this GitHub location. It's a non-intrusive header. It's only a header-only IOC container for C++. It provides the dependency injection tools that we need, and it spares you the trouble of writing and maintaining boilerplate code. So I've implemented this. I've used it in the application. It's being used in the test part of the application. Typically, this is the kind of code that you'll write. You'll instantiate a builder object, and you'll register your types. So it's quite fluent. You see, I'm registering a VOD server as the implementation of an iVOD server. So every time I request an iVOD server from the container, it will just spin up a VOD server and give it to me. So when you're finished with registrations, you then create a container. The container is the factory itself, which can be called anywhere in your code to resolve, that is, to create an object of the appropriate interface. How is that being used in CleanIt? Well, I've been using it in a number of places. I won't go into the details because I want to leave a little bit of time for discussion. So take a look at the IOC container tag, and you'll see how it's being used in the project. One other point I'd like to make before we wrap up and collect all the lessons that we've learned, and that is, I did mention inheritance a number of times, and I talked about the Liskov substitution principle. Well, the CPP core guidelines, C129 to be accurate, states that when designing a class hierarchy, you should distinguish between implementation inheritance and interface inheritance. So an interface inheritance is where you would like to expose on your method particular methods. You'd like to tell the world that your component implements a certain interface. This is a very important concept because it actually supports encapsulation very well. But implementation inheritance is in fact the opposite. You derive from an object in order to use its implementations. When you do that, you're actually doing the opposite of encapsulation. You're exposing your implementations to the outside world, unless you do a private inheritance. But as long as you're doing public inheritance, like I did for this project, you're actually saying that all the methods of the implementation are open to use right here from the object that I'm giving you. So it actually breaks encapsulation very significantly. So the guidelines say differentiate between the two. And I think that's mainly because it's so commonly used that the guidelines are not going to go out and say, oh, that code is not good enough. But I would say that you should avoid using implementation inheritance, and there are alternatives. The famous alternative is composition. You can use composition in practically any place that you actually need implementation inheritance. So here are just a few of the disadvantages of using implementation inheritance. Essentially, it introduces tight coupling between the actual object that you want to create and the implementation that it's chosen to use. An example of how I've resolved that in V7 use IOC container is actually I've created a logger which uses composition. Because the logger itself is really just a wrapper around some object that is able to write a string somewhere. It does some clever stuff with std format, it handles log levels and so on and so forth, but the real core of the matter is where to write it to. So as you can see in this logger that is implemented here, it takes an ilog writer injected into its constructor as a shared pointer, so that it can store it and be assured that it will be available when it needs to. And then in the implementation of write, it just simply calls the write method of the writer. So in this case, you can see I've used, instead of deriving from something or implementing it myself, I've actually used the core object that I want to use using composition. And that's a typical, I would say, solution for implementation inheritance. Finally, a few notes about modules. And I left this to last. I would like to explain why. I made 2 extra commits in the repo that you might be interested in looking at. One is V9 is to use header units for all of the STD headers that I was using. It does, in fact, speed up compilation times quite a bit, though it's not a very heavy project, so it's difficult to see. And then I actually made the VOD itself as a module, and I made all the changes necessary to make that work. Why did I leave it to last? Because unfortunately, the support for modules is not quite complete in all the toolings that I use. ReSharper doesn't support it yet, and therefore it made it difficult to develop the rest of the project while I was using modules. But it was important for me to demonstrate that it's possible, and you can play around with it, and you can see for yourself how it works, even across a DLL barrier. Let's sum up. What lessons have we learned? So, as I mentioned at the beginning, I think we should certainly adopt the CPP core guidelines for specific guidelines about C++. But I also recommend we continue to use the solid principles to guide our design. And we've done that in the course of this short walkthrough. Organize headers to reduce coupling. And I still think this is relevant. But use modules for new projects. And I think the tooling will improve, and we'll be able to see the benefits much more clearly in the future. Consider using standard expected for expected errors when it comes out. Consider using generators for lazy iteration. And there are, of course, other abstractions I'm sure you'll find useful in the libraries, in the CPP Coro library, for instance. Avoid primitive obsession. Use strongly typed domain objects that can validate for you their invariants. And that will save you a lot of validation code. Use interfaces on component boundaries. It's a very good encapsulation method to hide implementations. Inject implementations using inject the implementation dependencies using constructor injection. That doesn't necessarily mean you need to use an IOC container. It's still useful to explicitly mention your dependencies through abstractions, even if you can't use an IOC container to compose the objects. But consider the use of an inversion of control container like the one I have been using here to construct those objects. And finally, prefer composition over implementation inheritance. So, oops, we have 11. Well, actually, there are many more, and there are even many more that I mentioned. It's rather a short time in 1 hour to try to encompass all of the aspects of clean code, even in a simple project. So what I hope we have achieved today is, first of all, I hope that I've emphasized to you the importance of using clean code and the basic principles that enable us to make clean code. And second of all, offered you some tips, or at least food for thought, on how you can make your own code cleaner. Thank you very much. So I believe we do have a few minutes for discussion, 5 minutes. And please take the mic if you have a question.
Question from Dennis Bahadur. Is the movie object really always valid? How about a moved from movie object? Don't you have to make sure to still have a valid movie object? On this case, by providing specific move constructors / assignment operators.
I think the answer to that is yes. But if I'm not mistaken, because I have, the guideline says actually that I do need to specify explicitly all of the specialized functions because I have my own destructor. But I didn't implement that on this class. But I think you're right. Any constructor or assignment operator that actually builds the class must do the same validation, yes.
I have a question.
Yeah.
So I find sometimes like an inversion of control like solution is a bit heavy compared to using like default arguments to wire up for testing. I know it kind of exposes sometimes objects in the header. Not such a problem in some other languages, but would modules help with that? Would it be possible for modules to hide some of those details and still use like default arguments instead of like having an IOC container wire up your objects and graphs?
I would need to see the particular implementation that you're proposing for this, but my understanding would be that it doesn't really solve the modules wouldn't solve the problem here, because I understand that if you're providing a default argument, then the type of that default argument needs to be explicitly specified, and it's a type. And if it's not an interface, then it's going to be explicit dependency on the type that you're providing.
Well, no, it's just like you use like a default argument to inject like the concrete type, and then when you mock, you explicitly use another type in the constructor.
Oh, I see what you mean.
To be a bit more simpler than using IOC.
Okay, one thing I will mention, I think it's a good question. I think that would work,
Okay.
because you're using interfaces, but one thing I will mention is that IOC containers are much more scalable than what you're proposing. Because what I didn't show here is that you can actually create many types and not add any code in order to inject those dependencies into the code. The IOC container will do it for you.
It's only for testing. Like if you want to use IOC for like configuring your application, it's an excellent tool.
Right.
But sometimes maybe a bit heavy when you're just injecting for testing.
Okay, the only thing I'll mention with that is that very often, only for testing is an indication of how the application is going to be used.
It does come out, yeah.
So you start with the testing, and then it becomes something much bigger, and then you do need the IOC container. Thank you very much.
I have a question.
Yeah.
Over here. Thanks for a good talk. Regarding number 11, do you see this also like as a slippery slope that could lead to the call super anti-pattern being used more extensively? And then regarding number 7, are there like other important code smells or anti-patterns that you feel are very important to consider?
I don't think we have too much time to answer that. Do I have a moment to answer this question? Yeah, okay. So number 11, we'll answer number 11. Can this cause, the question was on number 11, can this cause excessive use of calling the base class? Is that was the question? Okay, I'm not quite sure why that would do that. Why that would do that? Because in terms of composition, you are composing an object that is provided into this class. There's no inheritance involved, so there's no calling back.
No, I mean the opposite. Like
I see.
Yeah.
Oh, I see. When you're using composition, this could call that. Yes, definitely. I don't use it too much, so I don't really have much experience. I try to avoid it at all costs, but there are many problems with, certainly many problems with using inheritance for implementation. I think we have to end here. I'm available after the talk if anyone wants to come over and talk. Your insights are also very valuable. Thank you very much.